Okay, so this was the original 2020 Christmas lecture, but then there were, last year, last December, there were a number of problems that prevented us to organize this properly. So we decided to postpone it to today. And of course, we call it the New Year's lectures. And this so some sort of sets the beginning of the new activities of ECLT for this year. So hopefully this will be much better than last year. So you may have noticed that, in the program, following up this lecture, there will be a focus on a presentation of the European Horizon Europe project, which is coming up in April. And this is because the reason for doing this is because this 100 billion euros program, research program, which will have a major impact in our scientific life for the next 7 years, I guess. And so we thought that maybe it was proper to sort of organize something and get started to learn this. So I should thank our Ka-Foscari Research International Research Office who agreed to give to share with us their broad knowledge about this program. So that said, let me now exploit the full privilege of being the director of ECLT, introduce the speakers today, who is Professor Mathew Diamond from SISSA. Mathew is a professor of cognitive neuroscience at SISSA. He's widely known for his many contributions in the field. He earned his PhD in neurobiology at the University of North Carolina, and then he moved first to Brown University and then to Vanderbilt University. And luckily for us, the governance of SISSA managed to attract him in Trieste, where he's now the head of the Tactile Perception and Learning Laboratory, and he's also currently vice director of SISSA. In addition to being a prominent scientist, Mathew Diamond is also, very active in outreaching activities, as all, the general staff in SISSA are. And he's also, in this respect, let me mention that he's the co-author of this new edition of the book From Neuron to Brains, that now is regarded as a classic in the field. And I think it was just published last month, the 5th edition. So this
sixth edition.
The 6th edition, okay.
And published on January 1st, so that the date is 2021. It keeps it keeps it fresher.
Good. So I just made sure that our library has ordered this.
Good, 100 editions, please.
Yes, yes. Okay, so that said, let me ask to all of you, please, to mute your mic in such a way that we don't hear any background noise during the talk. If you do, of course, have questions, which are mostly welcome to do, I guess. Then you feel free to unmute yourself, but then go back to the muted after the questions. That said, Mathew, please, the virtual floor is yours. Thank you for joining us and for accepting our invitations.
Yes, thank you very much for the invitation. I'm very, very happy to be here. I've followed a number of the ECLT seminars and found them all intriguing. And I personally and all of SISSA are very delighted to be part of this network. If you have a question as I'm talking, if something isn't clear or doesn't make sense, then you can turn on your microphone and speak, or I might, if you go into the chat, then maybe I see a little red flag, but I may or may not notice that. But in any case, find in some way, make yourself known, and I'll be happy to stop and talk about anything that comes up. And so this is an attempt to unify diverse forms of perceptual memory, and then from our the understanding that we think we're gaining about memory, we feel that we can go in new directions, which I'll end up in at the end of this talk. So, the topics that I want to talk about are rats and their whiskers, then memory. I want to go into memory, the neural networks for memory, and the way in which we try to tie together different kinds of memory, and then how memory has led us into the future. And finally, maybe most relevant to what do they call it, the next European budget. It's not called Horizon now, but it's called something else, I guess. And is there any usefulness for this neuroscience? And I do basic neuroscience, but there's always more and more, as I think we'll talk about in the next meeting, more and more need to actually find to solve the problems of society with the most basic research. So that's one of our challenges, is to make ourselves relevant to the society that wants scientists to solve problems. So for me, the research all began with rats and their whiskers. It's a really fascinating and intriguing sensory perceptual system. All rodents have whiskers that they move backwards and forwards to explore and understand the world. And this is sketches of some of the many behaviors that rats do with their whiskers. They can localize objects, detect them. They can feel textures, which I'll talk about again in a moment. They can feel the size of openings, called aperture discrimination, and much more. I could fill the entire page with one after another figure of the amazing things that rats do with their whiskers. So in our own experience, a lot of the research was done by Yanfang Zhuo, who was a postdoc with me and is now at the Institute of Neurosciences at the Chinese Academy of Sciences in Shanghai, and did a number of studies about texture. So these are some of the stimuli that she used, and she measured the capacities of rats using their whiskers to identify in any given moment without visual cues or without olfactory cues. We were careful to make sure that the only sensory modality available to the rat was touch. The rats were able to identify these textures, and the capacities that they have to make fine differences between textures that are very similar to each other is comparable to what humans have with our fingertips. So it's the sensory system is very different. Whiskers are very different from skin, and yet they accomplish approximately the same acuity that we have with our fingertips. And I don't know if Rolf Pfeiffer made it to the meeting. He sent me an email and said he would try to join the meeting. Rolf Pfeiffer is a member of our network. And many years ago, we had a project, and this is sort of a call out to him. This is how rats actively explore with their whiskers. This is done under infrared light. And he's using his whiskers to feel the texture that you see before, these grooves and ridges. And he's able to identify it through this contact. With Rolf Pfeiffer, we had a European project kind of back in the days when Europeans funded very basic research to try to figure out how rats do this. And Rolf's role was actually to make a robot that moved its whiskers and felt the world. And those, I think, proved to be very interesting and successful. And so from textures, we more recently moved to another field of tactile perception, vibrations. And we reasoned that it would be something that would be very important in the natural life of rodents. The most dangerous moment for a typical small rodent is coming out of his tunnel. Mostly they're safe in the tunnels. There may be a snake that goes into a tunnel to find the little animals, but by and large, they're pretty safe in their tunnels. But when they come out, they're exposed to the world. And we imagined, without really any scientific evidence, this is a sort of fantasy drawn by, if you can see the cursor, I'm indicating the person who made this drawing from SISSA Mechatronics laboratory, Marco Gigante. What we imagined is that a small rodent might feel vibrations that come through the ground as a large predator is walking around the nest system, and that this might be a warning sign. Of course, there wasn't really any proof of that. We know very little about the natural life of small animals, but it seemed to make sense. And I read much more recently that there are variations of this that have been found recently. For example, among kangaroo rats, they have a society where there's a scout who is assigned the dangerous job of coming out of the first one to come out of the tunnel. And when he comes out of the nest, he sends signals into the to the rest of the colony by thumping on the ground with his foot, and these vibrations are picked up by sense of touch. So our fantasy was, in this case, not exactly the same one as reality, but sort of a variation on the idea that rodents pick up vibrations through their sense of touch. This is perhaps more relevant to the modern world, to the densely packed cities. They're full of rats, and I again don't have scientific proof of this, but I would bet almost anything that rats in their natural environment, which is the subway system of New York, feel the arrival of trains, in this case the romantically named A train, by picking up vibrations, probably through their finger pads and also through their whiskers. So it seemed to us to be a perceptual capacity in which rats would presumably have good acuity, and that it was worth studying. So we brought this into the laboratory, and this led us into memory, because how can we go about studying sense of touch for vibrations? It turned out to be the most suitable task was a memory behavior. This was designed by and built by a PhD student of mine, Arash Fasihi, who is now in San Diego. And what we tried to do is bring vibrations into the laboratory. So this is a sketch of a rat who has learned to put his head exactly in this position and his whiskers exactly on this plate. And the plate is controlled by a motor, which delivers computer determined vibrations. The rat feels vibrations, and then he has to make a choice to go to the left side or right side. If he makes the correct choice, he gets a reward. And the choice is determined by through a memory task. So this is what it actually looks like. This is the actual photograph of the apparatus. And the rat puts his head here. His whiskers are in contact with this plate. The motor delivers vibrations to the plate. And when the rat receives the stimuli, he has to make a judgment. He gets a go cue, which is an acoustic cue that says, okay, you can leave the head hole. Now it's time to get the reward by making a choice to left or right. And this is what it looks like as a rat withdraws and makes his choice and gets a reward. And we were able to set up the identical experiments with humans, exactly the same stimuli, exactly the same paradigm, but they received the stimulus to their fingertip instead of to their whiskers. And this brought us to memory, because we considered for a long time how to study acuity, and we decided that the best paradigm would be a memory task, in which on every trial, the animal receives two vibrations, stimulus 1 and stimulus 2. And the task of the rat is to feel the vibrations and then judge whether the second is bigger than the first or the first is bigger than the second. And that relationship, stimulus 2 bigger than stimulus 1 or 1 bigger than 2, determines the reward side. And this is your visual system, not your sense of touch, but your visual system in this case can see the vibration and can see that stimulus 2 is clearly bigger than stimulus 1. This is a more difficult trial. And by measuring the choices of the animals over many, many, many thousands of trials as a function of the difficulty, what comes out of the experiment is an analysis called a psychometric curve. So the psychometric curve considers over many thousands of trials the stimulus range, which is the difference between the second and first stimulus. This is the speed of the mean speed of the stimulus, the second minus the first, normalized by the sum. And for positive values, the second stimulus is larger than the first. For negative values, the first stimulus is larger than the second. And the y-axis is the percent of the trials in which the subject judged the second as being larger than the first. So a perfect subject would look like this, a step function, because for every negative value, the first should be judged as larger than the second, And so the percent that follow this rule would be 0. And then for any positive value, 100% of trials would be judged as second stronger than the first. But of course, nobody's perfect. So what one finds instead of a step function is a so-called sigmoid curve, an S-shaped curve. And what one can measure from the S-shaped curve is the slope and the maximum values. So this is an okay psychometric curve, not great. This is a better one because it's closer to the step function, and this is even better. So what better means is that there are fewer errors for the easier stimuli, and it's very steep at the crossover point where the second stimulus becomes larger than the first stimulus. And these are the actual results from a large set of humans and rats done by my student Arash. And you can see that the rats are not quite as good as the humans, but they're quite close. And if one considers that rats frequently have a tendency to make mistakes on easy trials because they get distracted or they forget the rule or something like that, one can assume that in fact the sensory acuity is even closer to humans than what would be shown here. The ideal observer in reality for our experiment is not a step function because the stimulus is noisy. So even an ideal observer would make some mistakes. So this shows two properties that rats have that were not known prior to this experiment. One is a high acuity for sensing vibrations, and the second property is the ability to store information, store perceptual information, hold it in memory for comparison to a subsequent stimulus, which is a function known as working memory. So we worked on this for a number of years, and the experimental design for the working memory can be considered as a session which contains many hundreds of trials. And all of these hundreds of trials are broken into pairs, where in every trial, 2 stimuli are compared to each other. Then 2 more, and then the animal makes a choice, gets a reward. 2 more stimuli are compared, then 2 more stimuli are compared. And the important thing to note in working memory is that the boundary for making a decision, the choice boundary, is within the 2 stimuli. It's not a distant memory, it's a local memory, because it's only the most recent stimulus. If one considers this trial, the only information that matters as the brain is processing this stimulus is this stimulus. So the comparison is local. And what we realized a few years ago is that it would be interesting to generalize this to another form of memory, which we call reference memory, a term sometimes used in literature, where a session could contain the exact same set of stimuli. So nothing is different as far as what goes into the sensory system. It's the exact same stimuli in the exact same sequence, but the behavioral task is different. Here, each stimulus has to be compared to a fixed boundary, and individual stimuli, one at a time, independently of the neighboring stimulus, the next one or the last one, stimuli one at a time have to be compared to this boundary. So each stimulus is its own story. And now the boundary is something that's remote in time. It's not something that is evident within the last few seconds. It's something that's present for an hour throughout the entire session. So it's a reference point, a fixed boundary. And this is what a rat looks like when he does this task. He is first positioned in the same kind of apparatus to receive the vibration. He makes a choice, he gets a reward, and starts another trial. And again, we can do the exact same thing with human subjects, and I don't show the results from humans, but it was very close to that of rats. We again get a psychometric curve, and we again find very, very nice performance of rats where they have to judge this set of stimuli as being in the strong category. This set of stimuli ideally would be in the weak category. Again, the steepness of the psychometric curve is a good measure of performance. And this is performance that's close to humans. Now, the point that's interesting in this cognitive neuroscience literature generally considers these to be two very different forms of memory. Working memory is a form of memory that's the object of a lot of research in cognitive neuroscience, and such that there are even so-called working memory systems in the brain. There are networks within the cortex of the human brain and primate brain that are referred to as the working memory network, and it's believed to be a form of memory in and of itself. Very different from reference memory. And what we were able to do in the last year, actually, is to synthesize the results from a set of animals that did reference memory and a set of animals that did working memory. And then currently, with one of my students, Davide Gianna, a set of rats that actually does two different tasks on different days, which is something that I'm very proud of, because it's generally very, very hard to train rats to do two different behaviors in the same apparatus. But my student is able to do that. So they do reference memory and they do working memory. And considering the data together, what we've been able to do is to find a way to formulate reference memory and working memory as the exact same network containing exact same information, but differing only in which components of the network are read out or decoded or listened to or attended to in order to solve the task. So to summarize it very briefly, in reference memory, each stimulus, as you recall, is independent of the other stimuli. The task is done one stimulus at a time. The stimulus is encoded in early levels of sensory cortex. And that the representation of that stimulus in real time, as it happens, is compared to a decision boundary, which we've been able to identify as a long-term memory buffer. And we study this long-term memory buffer physiologically with electrodes. Meanwhile, the sensory code is also, the sensory representation is also loaded into a short-term buffer, and the short-term buffer and the long-term buffer interact with each other. They attract each other, as indicated by the magnet. Now, working memory uses the exact same network, but you recall that for working memory, the comparison is local. And the mechanisms are that the first stimulus within the pair is encoded, it has a sensory representation, and it goes into the short-term buffer, and it's held there as a working memory. A few seconds later, 2, 4, 8 seconds later, a second stimulus is delivered. It produces its own sensory representation, which is then compared to the short-term buffer. And this is the working memory decision process. It's a comparison of what you feel now to what you remember feeling from a few seconds before. And again, the short-term buffer and the long-term buffer interact with each other. This interaction is actually, which I've shown here, the long-term buffer is holding information for minutes or even longer. The short-term buffer holds the most recent stimulus. And it turns out to be exactly this interaction. Sorry, was there a question? So it's this interaction that allowed us to sort out that the two behaviors function within the same network. More specifically, what our experiments show is that the short-term buffer in working memory tasks is, someone has a microphone on, I think that would be convenient to turn that off. The short-term buffer, which holds the working memory, is attracted to the long-term buffer. And this produces a bias in short-term memories that has been known for some time. It's called contraction bias. And we were able to quantify that and show that the bias that the long-term buffer applies to the short-term buffer is exactly the same as the bias that the short-term buffer applies to the long-term buffer. This bias is seen in the fact that when rats or humans compare the current stimulus to the long-term buffer, it turns out that that long-term buffer, the reference memory, has been attracted to the more recent stimuli. Okay, so all of this is happening in both forms of memory, and the difference between two different forms of memory, which two memory tasks, which for a long time have been considered to be very different forms of memory, the difference is in which modules of the network are decoded and compared. Now, I elected not to show lots and lots of physiological data. It's not the most interesting thing for maybe for a general audience, but I do have the citations, the references here. And to make a long story short, without going into information theory and population analyses and all sorts of sort of detailed analysis, to make a long story short, my students and postdocs and I, for a number of years, have been using microelectrode arrays, as shown here in a healthy, awake behaving rat, to probe different parts of the cerebral cortex, and have been able to identify in a sort of computational quantitative way different regions of the cerebral cortex with different modules of this memory network. In particular, posterior parietal cortex is very strongly involved in long-term buffer, and we've shown optogenetically that we can we can manipulate the reference memory through manipulations of posterior parietal cortex. And very importantly, at least important to our own thinking, is that when we manipulate the long-term buffer, we find that short-term memories are actually stronger, they're more accurate. That was sort of a landmark, a big step in our coming to this model, is that we affected the long-term buffer, which in short-term in working memory should have no role at all, because the comparison, the memory is local. And what we found is that when we disturb the long-term buffer, working memory actually improves, because we've eliminated the attraction of the short-term memory to the long-term memory. So
sorry.
Please.
Okay. Yes. So maybe you mentioned, but I lost it. Is there a specific quantitative quantities that you can probe to distinguish the two regimes? Is that a time scale, or is it...
Yes. The way that the most robust way to quantify these are exactly by time scales, and we can measure time constants, which are the time constant for loading information into the buffer and the time constant for dissipating information. And what we see is that the short-term buffer is very quickly loaded. It has the information is dissipated more quickly, whereas the long-term buffer has a memory of tens of seconds. Okay, so we do information analysis to see what is what kind of signal is the population of neurons carrying, and we can correlate the signal carried by the population of neurons to the behavioral parameters. Okay, so now I want to go from past to...
question before you go?
Of course,
just
any question.
This talk about attractors has to be taken seriously, or is it just a way to present the material? So do you mean real attractor as, for example, a computational theorist would consider an attractor, or it's just to show that there is a relation between the two buffers and that is what is influencing, to have mathematical model behind or something like that?
We have mathematical models behind this, and what we think is that there is actual attraction between the two, because when we, for instance, if this is how one can envisage, by the way, was that Luca?
Yes.
Okay, I thought I recognized your voice, but I didn't see you speaking.
That's long-term memory.
Yes. So this is the, one can sort of envisage an experiment as occurring in this way. And if this is stimulus n-1, characterized by its amplitude or mean speed, and this is stimulus n, when stimulus n-1 is given in the short-term buffer, we see that we see the coding of this stimulus, and then we see the neuronal representation of the stimulus drift towards the value of the long-term buffer. And if we simultaneously measure the long-term buffer, we see this long-running value, which is very, by a slow time constant, continuously attracted to the last signal put into the short-term buffer. So these two regions of cortex, I went the wrong way. So these two regions of cortex are, we think not coincidentally, very strongly connected. This is a very famous parietal to prefrontal cortex connection. So these regions are directly connected, and we think that that's the physiological basis of the attraction.
Okay, thanks.
You're welcome. So this was memory, and then we are becoming more and more interested in the future. And we make decisions based on an explicit evaluation of the scenarios that might arise from alternative choices. This is the standard functioning of any living organism or any conscious living organism. When we have to make a choice, we think of what might arise from that choice. So a robust capacity in general to understand future scenarios, and here I'm using human terminology, but there's some form of this for animals as well. A robust capacity to understand future scenarios leads to an individual to informed choices and positive outcomes in health, in career, and so on. An inadequate understanding of future scenarios leads to impulsive choices and negative outcomes, substance abuse, dropping out of school, and many, many other different behaviors. Very relevant to our time is that an inadequate understanding of future scenarios also causes people to fail to protect themselves and to protect others from the coronavirus. So I think it's banal, it's a truism. It's not particularly interesting to say that we are at each moment made up of all the baggage that we bring with us, with our memories, so that our current experience is not isolated in time, but is a reflection of everything that has happened in the past. But it's perhaps a little bit less banal to say that memories are critical not only to the present moment, but to the future as well, because the future is built from our memories. Now, I don't intend to be only poetic here, but actually to go into some neuroscience. But let me illustrate what I mean by building the future from the past. So imagine that to this young gentleman, at some point, he's had an experience of skiing with a friend. In the present, this experience is a memory is a little bit foggy with the loss of some details, but this memory exists now. Suppose that that this person is faced with a choice about the future. Do you want to have another skiing outing? Do you want to come with us next month to go skiing? That choice would be based on creating a future scenario, which is called future thinking. Some people call it mental time travel. And that future scenario would be very strongly connected to the memories. The memories are a critical component, element, or ingredient of future thinking. Then an assessment of this future scenario leads back to the present, where the person makes a choice about something, whether to take skiing lessons, whether to stay fit, whether to accept to go on the trip, whatever. So the past is remembered, it's projected into the future to generate an imagined scenario, which then is used to make a current choice. So knowledge acquired in the past supplies bricks with which to build the representation of the future. So if we use the past to build the future, it might not be surprising that the brain systems involved in memory and recall, the same brain systems are involved in memory and recall and evoking such mental representations. So this shows two behavioral tasks that are given to human subjects, and the images are the brain activation measured by functional magnetic resonance imaging. And in one case, the subject is instructed in recalling episodes, episodic memory. This is the brain activation. And in another instance, the subject is asked to plan or imagine the future. And you can see that the brain activation is highly overlapping when remembering the past and projecting into the future. Memories, particularly in humans, but in other animals as well, I assume, memories can also be imported socially. So in the first instance, this person has his own memory of an event, which he can project into the future. But we can also imagine our futures not based on our own experience, but based on other experience. It's impossible for us to have enough experiences, a repertoire of our own experiences sufficient to make every future choice.
Pronto?
But we can gain knowledge from others.
Tranquilla.
Okay, someone should turn off their
Vabbè,
microphone.
comunque stavo guardando una roba.
Can you please mute your mic, Margherita?
Un secondo,
Margherita.
Okay, so we can have not only our own experiences, but we can import experiences from other people, and this is social interaction. So in this cartoon, a friend was sick in the hospital, and of course, to make it current, I show a sort of a COVID illness. She formed a memory, and she can now transmit that memory as an experience to this person, who then can incorporate another person's memory, not only his own memory, but another person's memory to imagine his own future. So now he substitutes the other person, creates his own future, and makes a choice about, for instance, COVID safety, whether to follow safety rules. Okay, so interestingly, I showed you a moment ago that the brain networks in humans for episodic memory and future thinking are very highly overlapping. And so is the network for perspective taking, that is for incorporating the experiences of others. So again, functional magnetic resonance imaging experiments have been done as the subject is instructed and guided in imagining him or herself being someone else, or in empathy and engaging in the experience of someone else. And in that case, taking the perspective of others engages a very, very similar brain network. So what is in common to these different instances of thinking? The hypothesized common function is that there's construction of a perspective different from whatever is happening right at this moment to you. And that change in perspective can be a temporal translation that is taking yourself out of this instant and inserting into your current experience something from the past, or creating a future experience. These are translations in time, or a social translation that is for a moment substituting someone else's experience for your own experience. So what's in common is to superimpose an experience that's translated either in time or directly from other people. And this is geographically, anatomically, this is the brain network that seems to be involved in that. Now, does this actually mean anything functionally? It does, because one very prominent form of future planning is delay discounting, the tendency to devalue rewards when their delivery is pushed into the future. And it's key to life choices. And these are the curves of a person who's less discounting, a patient individual. This is the curve of a person who's more discounting. And the more discounting means that when the person imagines some fixed value of a reward or benefit or a result that could be obtained in the future, an outcome that could be obtained in the future, when the person imagines that fixed value as being farther and farther in the future, the subjective value of that reward or that outcome decreases very, very sharply. And for the patient person, it decreases less sharply. So the impulsive person, if they want something, they want it right now, because in the future, imagining having that in the future doesn't matter that much. The thing has very little value when it's farther in the future. So delay discounting is interwoven with future thinking. It's a kind of future thinking. And for instance, my colleague in Bologna, Elisa Ciaramelli, has shown that whereas healthy control participants are able to imagine, to simulate, to create a future event like an upcoming party in great detail, and also are very proficient in intertemporal choice. That is, they are able to give value to future rewards. People with hippocampal damage who are not able to piece together details to create a future scene, or people with ventromedial prefrontal cortex damage who are not able to actually insert details at all into the future, in both cases, will have extraordinarily steep intertemporal choices. That is, they choose to have things right now rather than the future. Why? Because their future imagining, their mental time travel capacities are faulty. So the next question is there's a lot of territory, there's a lot of material here, and can we put this basic neuroscience to any use? We started with whiskers, but can we do something besides understanding whiskers, which from my point of view is all I would ever want to do, but I understand that it's worthwhile to go beyond the whiskers. So to go beyond that, one has to keep in mind that perceptual memory is a declarative memory component of episodic memory. Perceptual memory, that is a sensory experience that's stored in memory, is an episode which someone can make a statement about. They can describe it, so it's declarative, and it's a form of episodic memory. And so whereas in episodic memory in humans, we think more of events that have occurred, perceptual memory is, I would argue, and others argue, is a form of episodic memory that's restricted to sensory experience. And these cortical regions in rats that we have been exploring for a number of years is the exactly believed to be homologous network to humans. So what we think that we're studying in rats is the rat version of this same network. Delay discounting cannot be trained, but memory can be trained. So we can, in humans, it's not difficult. Many people know how to do this, to train people to get better in memory. And we know that we can train rats to get better in memory. And that's very different from training directly in delay discounting. There's no psychologist that I'm aware of, or that my colleagues who are more knowledgeable about psychology no one that I've talked to or read about is aware of a way to train people to say, I really want to wait for a reward. There are no exercises. There's no therapy that says, it's really worth it to wait because you'll really like what you obtain if you're patient. This cannot be trained, but memory can be trained. And delayed discounting cannot be trained, but memory can. Does memory training have an effect? And the answer is absolutely yes. A landmark study, 2011, from the group of Bickel, found that memory training reduces delayed discounting in addicts, in substance-dependent people. So if future thinking is fundamentally related to projection from our own here and now, then training programs targeting self and perhaps other memory should improve delayed discounting. So if you're still skeptical, then you would be interested in this new result, again, connecting to our COVID world. And individuals with higher working memory capacity exercise better COVID-19 social distancing. And that, I think, really points to this connection between ability to remember things and ability to understand the future. And if you, it's a connection that might not be completely intuitive. Why should being able to remember make a person more willing to protect themselves and others? The reason might very well be that a good memory is correlated with good future projection, good mental time travel, good simulation of potential scenarios, and a person who's able to simulate a future scenario wants to protect themselves more. So a better understanding of the past and future connection in humans and rats could shed light on COVID-19 mitigation and other challenges, and might also help psychologists treat individual maladaptive future thinking. Can we memory train people away from self-damaging and society-damaging behaviors? And from the work of Bickel, one can already be optimistic that the approach would work. So personally, where are we going from here? Well, we absolutely want to keep going with the perceptual memory studies. We still have a lot to do there, but we want to combine that, and we can do so in the same apparatus with future planning studies. And as I said, delayed discounting, that is choosing how long to wait for reward, is very much a part of future planning. It involves simulation of the future and has been shown in humans is very much correlated with the richness and detail of mental time travel. So we can train rats, we can have rats that do memory tasks. We can, I think, it's not impossible to have the same rats do delayed discounting tasks, because those are intuitive to rats. It requires very little training. You simply allow them to make a choice between an immediate small reward or delayed larger reward. And simultaneously, we want to measure neural activity and to verify in this model that the same neural networks that are involved in memory are also engaged in the rat doing future planning. An intriguing experimental design to me would seem to be to have one set of rats that does only the future, the planning task, the delay discounting task, and is exposed to the same apparatus, but without working memory training, versus another group of rats that does delay discounting, but also does memory tasks. And our hypothesis would be that the enhancement of the memory network in the memory trained rats would have measurable effects on delay discounting, and that we would be able to, in this way, actually specify what is exactly what is tuned in the memory network to allow the animals to see the future better. And so I think this brings us to the final point, which I think we come to in the next hour, which is what can basic science, what can we do with basic science, and what can basic science do for us? I've very much a basic scientist, and came to all this through rats and their whiskers, and never imagined that interest in rats and their whiskers would lead to COVID mitigation and things like that. But I think that there's a message that I wish our European sponsors could understand, which is that sometimes you can begin to understand a very practical, important problem in society beginning very far away, because you don't know where the basic research is going to go. Sometimes it remains very basic, but sometimes it can shed light on practical problems. So with this, I conclude, and I thank you very much for allowing me to join this meeting. Thank you.
Okay, thank you, Matthew. I think you can hear or can see the virtual claps that we are.
Okay, good. Thank you very much.
Yes. So are there any questions? If you have questions, please unmute yourself and ask the questions. You're welcome to do so.
Yeah, I would have
Yes.
two questions, if it is possible. Nobody else. Okay, first of all, very beautiful talk, Matthew. Thank you very much. It's
Thank you.
very good. And it overlaps, that's why I'm asking with some of the issues that I've been interested in, which have to do with how infants can imagine future states.
Yes, yes, yes. Beautiful.
And infants are particularly interesting here because they have little experience, therefore they have little memory in terms of what they saw. So my first question, which I think is really important, I mean, I'm happy to see that you are more philosopher than neuroscientists, because what you are touching are really things that have a lot of connection with the fundamental concepts. And one of the things that you pushed a lot is this idea that essentially knowledge acquired in the past is what you use to serve for predicting future.
Yes.
This is one interesting. Now, the point is that, and that's the question that I have is, how much do you think this is an exhaustive model? Because it turns out that, so there are two ways to think about this. One has to do with essentially efficiency. So if you want to save time and you already have had an experience, your best bet is just not to think about the future, but just project previous experiences into the future. And then you don't have to reconstruct or to make up, quote unquote, a mental model of the situation in which. That's one possibility. The other possibility, therefore, this does not exclude the fact that really thinking about the future is another kind of phenomenon. Only you don't think very much about the future when you have past experiences, because that allows you to actually import information. So it saves time. The other possibility is that, therefore, there are two ways in which you can think about the future. One is the lazy way, which is the memory network. The other one is the committing way, which is essentially to make up a construction of what could possibly happen, even if you have no experience. That requires frontal lobes, lots of efforts, planning, and so on, which you don't necessarily need if you import information from the past. So the point is there is a possibility that you have two different kinds of systems to predict the future. One based on experience, the other one based on reasoning. The alternative theory is the theory that says, no, you really need experience, and you really need, for example, social information in order to make up models of the future. These are really two different theories. They also have different predictions in terms of what neural circuitry are involved in this kind of task. And my question is, which one do you think you are holding here? One which says there are two different systems to predict the future. One is memory based, this is what you describe, and then there is another one which is essentially, as it were, combinatorially based, in which you don't know anything, you have no experience, but you have some sort of basic understanding of how the world works, and you make up your mind. Or else you are really serious about the fact that you can't really have a future prediction without importing some knowledge acquired from the past. That's the first question. And the second question is not really a question, but it's an observation. And there is another part of your talk which overlaps with what I'm interested in, which has to do with delay discounting and this point that they cannot be trained. I think you are right.
Mm-hmm.
However, there is a parallel literature which may be interesting also in terms of making up remedy systems, which has to do with training inhibition.
Mm-hmm.
And this we know a little more. So inhibition is important there because prepotent response is essentially what leads people to just discount very much things that you shouldn't discount. Yeah.
Yes.
And there is some little extra positive advantages, because we do know that there are some ways in which you can train partly inhibitory, and this can be done by education, for example, or even by just practicing certain sports.
Mm-hmm.
Or by practicing bilingualism, for example. This has been claimed as well. And the point about that is that if this kind of literature of kind of systems are relevant to what you're trying to argue, then then it's the way you would need to do some sort of practical kind of operation to improve delay discounting is different. So, for example, it's known that just improving memory, studying, it doesn't help you being a better inhibitor of prepotent responses. Okay, so these are the two. One is the question, and the other one is
okay, good. Yeah, thank you for that. Those are both really right on target, and they taxed my working memory to keep track of everything you said. But I have to really begin with a disclaimer, because my expertise is computational neuroscience of perception and so on. So I'm learning. I've consulting with a research group, and of course, like everybody in Italy, a few days ago we submitted a print together. So in the course of preparing this grant, I tried to learn as much as I can. But the questions really are, your questions are really for an expert psychologist. But let me say what I think I've understood from the group that I've talked to. Of the two alternatives, I think that our group would come out very strongly in favor of the second alternative, namely that there is not really a future planning that is divorced from experience. In none of our discussions or the articles that we talked about or the writing of the project, in no case was there discussed a neuroscientific, psychological scenario in which a person can take knowledge to create a plausible future, a mental time travel, a future simulation that's not based on some kind of stored information memory, which could be either, as I said, one's own experience, or because we're social animals, it can be knowledge gained from others. So that our point of view, I think, as a group, is that memory is really inseparable. Memory is what you know. You know something because you remember something, and this combinatorial reasoning that you described, I don't know what could be the ingredients of the combinatorial reasoning, if not something that you've information that you've stored. It's true that with the memories, you have to create some kind of a scenario that includes complex combinations of different details. If you're planning an event, you have some memory of other events, but then you think, well, there may be other people, and some of the other people that came last time won't be there. So there are many combinational events, many combinations and permutations. But I think the consensus of at least the people that I'm talking to, is that there would not be a future simulation that could be fully separated from memory. They're very, very closely bound together in these. Then the other one, oh yes, the other point was making choices not only in relation to future simulation, but also in relation to impulsivity, and that's a very, very good point. And the psychologists that I've been talking with the last month are pointed that out to me, that we have to make this distinction. they are physiologically, it's been shown, different systems. This impulse control, this inhibition, is not the identical system as the future simulation, which takes the memory system and makes a projection into what the future may feel like. That is different from the impulse control, from the inhibition. You're absolutely right about that. There's, executive control systems that are involved, and so the making a choice in the future depends both on creating a rich, detailed, doing it well depends on creating a rich, detailed scenario of what that future might be, considering permutations and combinations, a very heavy cognitive task, combined with controlling impulses for getting something faster. So I think the two things combine, and it's a very good point to that you made about the distinction in decision making. They're not the identical system.
Okay, thank you very much. I think you are wrong on the first point, but it's very interesting.
Okay,
So I'm very happy.
We should talk about that offline.
For the second point, I think it would be really, really nice now that you're thinking about programs, maybe to make the point of, say, different kind of regimes of training, one of which is very memory based,
yeah,
one which is very executive control based, and then what you're going to do are your tasks. If you consider this duality of systems which are involved, then you can also consider a better way to enrich potential programs to improve people or rats, whatever. Yeah, but great. Thank you very much.
Okay, thank you, Luca.
Okay, there is another question from Maria Manone. Maria,
Yes.
please.
Okay.
I can see it in the chat, but you can say it by voice also.
Okay, thank you so much. Really enjoy your talk. It's a fascinating topic. I just have a couple of quick questions, one on rats, the other ones on humans. So I was wondering if it is possible to develop also non-invasive experiments to get information about how the brain of rats is working regarding perceptual memory. The second question is regarding humans, because I think that memory is playing a fundamental role, and also in decision making and so on. So I was wondering if it could constitute some kind of bias towards creativity or an advantage.
Yes, so as far as the first question, it's possible to study rats and learn a lot about their behavior in a non-invasive way. I think by invasive, you mean, for instance, not using electrodes, not using physiological measures. A lot can be done. We frequently do psychophysical experiments in rats that don't necessarily lead to the final invasive step in the experiment, but there will always be a limit to the knowledge that you can gain if you exclude invasiveness, invasive methods. So in our laboratory, we do a kind of research in which there are very, very few rats used. If you compare it to, let's say, pharmacological research and things in that field, the number is orders of magnitude fewer. We use in total 16 to, I'd say around 24 to 30 rats per year, including all of my students together. And in each individual animal, there's an enormous investment. We work on an individual rat for many months. But if we want to find out the actual functioning of the neural networks, we have to get to the invasive step, which means measuring electrical activity of neurons and manipulating neuronal activity through optogenetics. But what I can say is that my students are absolutely dedicated to the well-being of the animals, and they're visited every day by the students, by the veterinarian, and extraordinarily high levels of care are given to them. They have exercise rooms, they have social meeting rooms. I mean, not just the students, but also the rats. And enormous efforts are made to make sure that they're not harmed beyond the insertion of the electrodes. But the answer is that it's not possible to learn about the brain without seeing its activity during behavior. Could memory constitute an advantage or a bias towards creativity? That is goes into fields of psychology that I don't have expertise in, but my intuition would be certainly yes. I mean, we can go back to Luca and Luca Bonatti, who might comment on that, but my feeling is that memory is an advantage towards creativity.
Thank you.
Barbara del Mercato.
Yes, actually, I'm very hesitant to ask a question because I absolutely don't have a scientific background, and so it's like walking on thin ice. I have a more literary background, but I was fascinated by your talk, as often hearing someone speaking from completely different realm can.
May I ask what you come from?
I have studied literature. I work for the Center for the Humanities and Social Change, and I have a background in literary studies.
Mm-hmm.
And so my question is connected to Maria's in the sense that she spoke about advantage or bias towards creativity, but my question was, you speak about memories as in some way, some sort of package that we can move into the future to use for.
Did you say a package? That
yes,
we can
a little
okay.
object that we can take and somehow visualize in the future so as to affect our present behavior or our decisions and so on. But what about our lies, all the lies that we tell ourselves and all the lies that our body tells ourselves? I'm thinking about, for example, memories of pain. When you give birth, they tell you that you're going to forget the pain that you have experienced while delivering a baby, so that, because if it weren't like that, nobody would have a second child.
Yes.
And when I had the child, I thought, this is impossible that this is going to happen. I will never forget this.
Yes.
And of course you do. I did, like everybody else did. But more generally, I have the feeling that our body can lie to us in every single moment. I'm not speaking about the lies we tell ourselves sort of consciously, but the ones that our body, for example, performs on us. And so I have the feeling that in every use that we make of our memories, we should take into account the fact that our memories are not neutral. They're always also a product of more than just what happened, but what we put into what happened. And that when we try to move that thing from the past into the future, this aspect has an impact. And of course, I guess all the literature comes from this kind of reasoning too. But so I just wanted to chip in this little doubt that I have and see.
Yeah, I think these are really interesting questions. I never went through childbirth, but I had a very but what you say reminds me of my own experience when I was a young guy in school. I was a long distance runner. Everyone did some in the United States. Everyone did some sport, and that was my sport. And when we were in the competition in the race, 10 kilometers or something like that, at a certain point, I would say, "This is insane. I am the pain that I'm feeling as I take my body beyond its limit is unbelievable. I'm going to finish this race, and I swear to God, it's the last race I'm ever going to do." And then I would cross the finish line, and within 10 or 15 minutes, I was saying, "Okay, let's, we got another meet next week. Let's get ready and train some more." And you're right, the pain and the decisions made during pain are not durable. And I don't know why that is, but as you said, if it were that way, there are many things that we would not be able to do repetitively. And that's also true for, I think it's also a component of maladaptive decision-making. I just finished a book by a very brilliant musician named Mark Lanigan, who had gone through most of his life from the age of 14 to up to I don't know, to 30 something as a very, very strong drug abuser. I mean, very, very big time drug abuser. And he would be extremely sick multiple times. And then when he got over the sickness, that really didn't, even the way he describes it, you can see that when he felt sick, it was not a good experience, but he could not, in his memory, he could not really give any emotional weight to that. When he wanted to start the whole thing again, the value that he attributed to the experience of being sick was not enough to keep him from starting again. So in a sense, not being able to give the impact or the weight or the emotional value to negative experiences is a kind of maladaptation that can lead to repeating them. So it's really interesting. I don't really have, of course, now we create false memories and remember things incorrectly for sure, but I think that the memory is what it is, and then that's what you use to make the future projection. For instance, you may have had a miserable birthday party because you don't like being in the center of attention, but then someone says, okay, let's plan the next one, and then you sort of trick yourself because people expect you to do it. You trick yourself into thinking, well, you know, it's not that bad. Let's get together and work on this event. So yes, we trick ourselves, we lie to ourselves, but all of that that's part of the memory that I think we use. And then there's a question from
Stefano, yes.
Stefano, what happens to rats when you finish experiments? As I said, we study very few rats and we invest enormously in the individual rat. My students have very close relationships with each of the animals that they study, and each one has a personality and that my students get to know very well. And they study them for up to 2 years, if you believe it or not, which is I think pushes the life expectancy of rats. So what happens is that basically the rats get very old, and the rat at a certain point becomes unhealthy just from aging. They get old basically, and when the rat gets old, we can see that he's not healthy. He doesn't eat properly. He doesn't groom himself. And then consulting with the veterinarian, we say, okay, this rat has reached the end of, he's becoming stressed from his aging problems. He doesn't move properly and so on. And then at that point, we kill the rat. It's with a drug overdose, if you want to be very explicit about it. Is that kind of your question?
Yes.
Okay.
Yes. There is another question by Bea de Gelder.
Yeah, can you hear me? Hi, Mathew.
Yes, I hear you. Hi.
Hi, interesting talk. Just a comment which may speak to some of the questions we've heard. In moving from animal memory studies to human memory,
Yes.
there is, of course, I mean, there's a big gap. There is
Yeah.
things that transfer, things that don't transfer. But one thing that strikes me in the questions and the comments is, and you seem to sort of go along with that, and I would like to hear your view about that. I mean, we humans don't really have, we talk as if we now were memory, but that's of course extremely misleading. I mean, there are like layers and different, you are probably right in objecting to the notion of different memory systems, and some of that can be collapsed and will be collapsed in future research. But still, for me, I think it's important to notice that our memory, like the rest of our brain process or visual perception, we don't have a read out of that. I mean, we don't know what's in our memory, so to speak.
Yes.
And we reconstruct what our memory is, but that's, I mean,
Yes.
our body carries memories that we don't know about, that we don't have access to.
Yes, I agree. I hope I didn't say anything that made it sound like I don't believe that. I mean, we encountered that very directly in our research because we did this what I called the reference memory task. We did with rats and we did with humans, where you receive a stimulus and you have to classify the stimulus as being in one or the other category. And what we imagined going into the experiment is that this category boundary is in memory. that you remember a boundary. And then we went through a lot of analysis of the data, which I won't explain at this point.
Yeah.
But what the analysis showed is that the memory, what you think of as being the memory, is actually a sort of a moving average of the stimuli that you've recently encountered.
Yeah.
So the boundary, there is no such thing as a boundary. When you as a human or you as a rat receive the stimulus, and the task is decide if the stimulus is in the strong category or the weak category. Is it above or beyond or below the boundary? That's not how the task is solved. It's not following that logic. The way that the task is solved, it turns out, is that you get the stimulus and the brain is saying, is this stimulus strong or weak? Well, strong or weak compared to what? What do you mean strong or weak? It's compared to a set of recent stimuli, and we kind of worked out computationally how those stimuli are put together and weighed. So when you classify stimulus, you're saying, is it stronger than recent stimuli? That's the entire computation, at least under our experimental conditions. So something that you might think logically is a memory, there's a boundary, there's a line. It's not, that's not what the brain is doing. It's storing the recent stimuli and comparing the current one to the recent stimuli. So yes, there are many sort of hidden functions.
Does that not make the contrast that Luca Bonatti made between two ways of constructing the future a little bit artificial? This looks much more like a sliding thing, or
well,
it's not an either or. It's not like we construct a future based on memory, or we construct it based off de novo. That's a bit of a false contrast.
Yes, I don't know. Luca and I agreed to talk about this more because he said he disagrees with my memory-based hypothesis, and we're going to talk about that offline and try to sort this out. So as I think the non-memory based future projection is something that Luca could tell us about in a future seminar, but I'm not qualified to do that. For me, it's very difficult to imagine a future. I mean, you could make a future. I could give you data. I could provide you with a set of data parameters and terms and say, this is what's available now. Imagine a future scenario based on the information that I'm giving you. Well, you don't have any memory. I'm saying I'm giving you data and saying this is what's available, make the simulation. And I suppose in that way, you could create a future based purely on reasoning without having ever directly experienced any of these parameters.
Or you can be an infant and have now not much of an experience, but have to think about what's going on in the world. And that is, but I don't know if anybody is there, but if there's nobody there, can I just make a little point?
It's up to Achille, who's keeping us on schedule. And
I'm enjoying this. Maybe we should arrange another meeting with the talk by Luca. In fact, we should do this. Please go ahead, Luca.
We will save another time. I just wanted to say that maybe it's a continuum. That's possible, totally. However, it's true. I mean, people who studied, for example, frontal lesions remark this fact that very often the subjects maintain a good memory of their past, entirely good memory. However, they're totally unable to plan correctly the future. So maybe there is a little more. Now, this is not a strong argument. It could be that, the very fact, I mean, you don't actually know. Maybe you just break the connection between the memory system, as it were. Maybe you have broken whatever, the attractor. That doesn't mean necessarily that there are two systems. However, there is evidence that suggests that, at least to a first approximation, when you think about the plan, so when you play chess, you might play chess by just considering all the configuration of the board that you have seen in the past, or else you can just make up a novel plan. Okay, so these things seem to be like phenomenologically at least different, but I stop here. So.
No, as we're as the conversation progresses, I more and more understand this point that you're making of a non-memory based simulation, just based on data, on parameters, on chess pieces. Yeah, I get that point. That's interesting, and I hadn't thought about that. Thank you for the discussion.
Okay, thank you. I think it was a very nice, very lively and nice discussions. I don't see any. Are there any other questions? I don't see anyone. So if not, please join me to thank again Matthew for this very, very fascinating talk and topic.
And even make a real clap.
Yes, virtual clap. Yes.
Thank you. Thank you, everyone.
Yeah.